Well, welcome back to Geography 212. This week we're going to talk about cloud formation and precipitation. All right, first of all, in terms of cloud formation, there is one essential ingredient besides water vapor, and it's what we call nuclei. We've talked about aerosols before, where nuclei are aerosols, all right? They're solid particles suspended in the air. Occasionally they can be liquid, but generally they're solid particles in the atmosphere. We'll get into this in a little more detail, but what happens is the water vapor will condense around a solid aerosol. Now, what are these aerosols? If you look down toward the bottom here, volcanic ash from volcanic eruptions. It can be soil, in other words, dust, soil, that kind of thing getting up in the atmosphere. Forest fires, when they burn the smoke, pieces of black carbon get up in the atmosphere. Ocean spray, when waves crash against the shoreline, they'll release salt into the atmosphere, these solid salt particles. All right, so types of nuclei. We're going to generalize and say there's two different types of cloud condensation nuclei. And the first type you can see is cloud condensation nuclei, has the acronym CCN. One way to look at this is warm cloud condensation, warm cloud development, because this is generally going to be produced in clouds that has above freezing water droplets. All right, so what happens is we'll get this cloud condensation nuclei up there, just like we had just described. It can be salt, dust, that sort of thing, and the water vapor then will condense and then turn into liquid on that CCN. Okay, now occasionally you notice I've got a dash down there. It said cloud droplets can remain liquid even at temperatures well below freezing. Well, they can. As a matter of fact, we've discovered that liquid cloud droplets can stay liquid down to around minus 39 degrees Fahrenheit. We call these supercooled droplets, okay? All right, anyway, most of this, staying with the CCN, most of this type of cloud condensation occurs in cloud temperatures above freezing. Not necessarily, but usually. So that's why I would refer to this as warm cloud condensation. All right, second bullet down, ice-forming nuclei, or the acronym IN. This is going to be what we call cold cloud condensation. We've got pretty cold temperatures in clouds like this, and when these either supercooled water droplets or just ice condenses onto our aerosols, they'll produce an ice crystal. So in other words, ice-forming nuclei are nuclei, they're going to form solid ice in the cloud, okay? All right, the role of nuclei in terms of cloud formation. I want to mention this a special category of cloud condensation nuclei. It's called hygroscopic nuclei. And what's important about hygroscopic nuclei, again, an aerosol, some sort of aerosol, is it actually attracts H2O gas molecules toward it. And so they're very good at forming clouds. I'll give you one example as I go down toward the bottom here. Salt, okay? And any sort of solid particle as a crystalline structure similar to salt will have this. In this example, magnesium chloride, which is really similar to sodium chloride in ocean spray, can promote condensation at low relative humidities. So in other words, very good at attracting these H2O water vapor molecules to become liquid. Now, you notice the last thing down here too, that cities that put out a lot of different types of air pollution, which are aerosols, can produce clouds more readily than cities and towns that don't have as much air pollution in the atmosphere. All right, cloud classification. Okay, so once we get clouds developed, we do have a classification system for them. And just to preface this, I just want to reiterate and emphasize this point that clouds are either liquid water or solid H2O, all right? They are not water vapor, they are not gas. H2O gas is invisible to the human eye. So we need to have condensation that produces liquid from vapor, or deposition that produces ice from vapor, all right? So cloud classification is really based on just two things. It's based on the altitude of the cloud base, and when I'm talking about altitude here, I'm talking about altitude above ground level. It's referred to as AGL. not above sea level, but above ground level. So the height of the cloud base above ground level. And we're only going to have three different names for that. It's either going to be low, which is strato, middle, which is alto, or high, which is cirro. All right. That's generally the first word of the cloud name. The second name is based on just one of two things. It's the cloud appearance. Okay. Is it puffy? That kind of thing with some vertical development, it gets the name cumulus. All right. If it's just layered and it's very uniform in shape, we call it stratus. All right. Now, the three things I have down here below also, a lot of times in cloud classification, we're not going to really know the exact type of the cloud, but we certainly should be able to know the height of the base. So, for example, in aviation, it's very important to know the height of the cloud base. So in the bottom section here on this slide, you can see that we could say it's a cumuloform if it's of low cloud, and we'll define low, middle, and high in a moment here in terms of numbers and height above ground level. But we could go cumuloform if we know it's a low cloud, stratoform, or cirroform. All right, let's get into this. Here's a cloud classification scheme. And if we look over onto table 7.2, we can see we've got high clouds, middle clouds, and low clouds. Let's start with our high clouds first. Now, the altitude of the base above ground level is given to you in meters. So, just to make sure you can interpret that back to feet, a cirrus, any high clouds or cirroforms, the cloud base minimum height is going to be 16,000 feet or 5,000 meters. Now, the 13,000 meters isn't quite as important because cirrus clouds will go right on up into the stratosphere, and that height can vary. But if you want 13,000 feet is around, or rather, sorry, 13,000 meters is right around 40,000 feet. Okay, so high clouds. So the first word, cirrocumulus or cirrostratus, the cirro part means it's going to be 5,000 meters or 16,000 feet minimum base above ground level. Now the second part, the cumulus or the stratus, is going to indicate the appearance of that cloud. So if it's a cirrocumulus, it's going to be lumpy. If it's cirrostratus, it's going to be uniform in look. All right, going down to middle clouds, the alto stratus, alto cumulus. Okay, alto is a term we use for a middle cloud form. The 2,000 meters is going to equate to approximately 6,000 feet above ground level. So in other words, alto cumulus clouds base then must be between approximately 6,000 feet and 16,000 feet. Again, like the cirroforms, the alto forms can take on either alto cumulus, if it's a lumpy shaped cloud, or alto stratus if it's a uniform in shape. Okay, low clouds, these are going to be clouds from right at the surface to 2,000 meters, which again is 6,000 feet. Now we do have, if you look right at the bottom, clouds with vertical development. It can be slightly different. The cumulonimbus cloud, and this is important actually, cumulonimbus cloud can actually go through all three of these sections. In other words, the base of that cloud can be in a low cloud situation, in other words, less than 6,000 feet above the surface. And the top of that cloud can go actually occasionally can punch through the stratosphere. So a cumulonimbus cloud, where we get our thunderstorms from, these clouds can go all the way up from near ground level up into near the stratosphere. All right, let's get into a little more detail on these. So here are your cirroforms, all right? Remember, base is above 16,000 feet. One of the really important things about these clouds is the second bullet. They are going to be composed, really, I would say, not almost, but exclusively of ice crystals. And that's one of the things that give them a characteristic appearance when you look at these photos down here, okay? So you start off with the one on the left, just cirrus. These are those classic clouds. They're very fibrous in appearance. You can see these very long strings, it looks like, in them. That's because they're so high above the ground. They're generally in very high wind speeds that just almost pull these clouds apart. All right, but then we have cirrostratus and cirrocumulus. You can see the cirrostratus in the middle photo. That's got a very uniform look to it. And then the cirrocumulus, you can see these almost individual lumpy clouds to them. So there's your cirroforms: cirrus, cirrostratus, and cirrocumulus. Okay, our middle clouds down around, between 6,000 or so and 16,000 feet. Temperatures are going to be a bit warmer, but still pretty cold. You can see that. The clouds can be a mix of things here, alto clouds. They can be composed of supercooled water droplets or a mixture of supercooled water droplets and ice crystals. And really just two types of alto forms. You got your alto stratus on the left. See how very uniform that look is? And you have alto cumulus on the right, but you see the lumpy shape to it there. Okay, so there's your alto forms, alto stratus, alto cumulus. Low clouds. Okay, these are going to take on the prefix of strato or stratus. And again, these are from Earth's surface, right at the ground, to around 6,000 feet. All right. Typically, these are going to be warm clouds, what I call warm clouds above freezing or near freezing. So they're going to be mostly composed of water droplets. All right. Now, the typical ones, the photographs here, stratocumulus on the left, and stratus, you can see sort of the difference there. The stratocumulus, the lumpiness to it. The stratus on the right is just uniform in shape, okay? Now, there's one other cloud, you might call it a specialty cloud. If you look at the third bullet down, it's referred to as nimbostratus. Now, this is going to be basically a rain cloud. Nimbo simply means rain. So if we have a nimbostratus cloud, these are thicker generally than a typical stratus clouds. These would be rain-producing clouds. And the last bullet down, in terms of precipitation, we're generally only going to get drizzle forming from stratus because these clouds are thin, and since there's not a lot of thickness to it when raindrops form, it's not going to have a lot of contact with other water droplets in the cloud to get very large. It's usually just very small droplets in the form of drizzle will come out of these clouds. Clouds with significant vertical development, you start in the upper left. Cumulus clouds. This is from rising bubbles of air from the surface. You know, the sun heats the surface heats the air rises, and then as it reaches 100% relative humidity, it's going to form water droplets. And if the conditions are unstable, we can see these cumulus clouds in the upper left carry on into the photograph below it, cumulus congestus. That's a cumulus cloud that's starting to have significant vertical development in it. And it's one of the stages to the picture on the right, the cumulonimbus cloud. That's going to be a fully vertically developed cloud that's reached almost into or to the stratosphere, the tropopause. All right. Okay, fog. Now, fog is simply a cloud in contact with the ground, okay? You know, and there is a definition for that. You can see if you're interested. Its visibility is going to be restricted to 3,250 feet or less, which is 1,000 meters. Otherwise, if the visibility is greater than that, we would call it mist or light drizzle. All right. Now, there's several types. The first type I want to talk about here is called radiation fog. And you can see in the photograph on the left, you see this fog in contact with the ground at a valley bottom, which is very typical. Now, typically the way radiation fog forms is at night on a calm, clear evening, typically in a valley. And this can happen certainly in the Prescott area, but if you're in a valley, clear, calm, the upper elevations will cool off more quickly than the lower elevations. The colder air is denser, therefore it's heavier. In other words, the molecules are closer together, they're denser. So that cold, dense air will start flowing off of the higher elevations and will flow down into and settle into the lowest parts of the valley. All right, so now you've got the coldest air down on the valley bottom, and it can typically reach 100% relative humidity in the coldest part of the valley there, and you can get condensation forming and the fog comes out. So in other words, the radiation fog is going to occur where we have something called cold air ponding. The coldest air on a clear, calm night in the fall and winter can be at these lowest elevations. All right, so that's when we're going to get radiation fog forming. Now, other types of fog here we have here called advection fog in this little graphic here. What this is they're showing you an example of over in the Great Lakes here. How if we've got warm air moving up from the south, and if it crosses that lake there that's very cold water, it will chill, condense that warm air and cause condensation. So it's only going to occur over that very cold water there. So advection fog. The other term for advection fog, or another way this occurs, is that actually that fog you see on the lake there could actually move horizontally into northern Ontario there, where it's moving toward in Canada. We also see advection fog moving off of the Pacific Ocean into the Northern California area around San Francisco. That water right off of the Northern California coast, that ocean water, is typically very cold at the surface. And if the air is warmer over top, that cold ocean can chill the air, and that fog then can move in the westerlies onto the coast. San Francisco gets a lot of this advection fog. Another type of fog, steam fog. There's other local names for it, Arctic sea smoke. This is going to happen similar to the other kind of fog, where you've got, well, actually, it's opposite in the sense that in this case, it's cold air over relatively warmer water. So again, this could be the Great Lakes, though. This could be when the Great Lakes are still not frozen, and we get a cold air mass moving down across that water. And when that happens, then we can get the warm water causing condensation in that very cold air as it comes over. All right, another type of fog, we refer to it as upslope fog. What this is simply orographic lift. So in other words, air is being forced up a mountain slope. Remember, as air rises, it cools and condensation can form. Okay, so typically these higher elevations, if enough moist air is moving in, is forced up to condense, we can get upslope fog in contact with the ground. All right, now we're going to move on to precipitation processes here, because we get the clouds up there. Now, how does precipitation fall out of clouds? One thing to start with, though, is that at any given time, Earth's covered by 50 to 60% of cloud cover, but very few locations where that cloud cover occurs is getting precipitation. So it turns out we can get a lot of cloud developing on this planet, but we don't get that much precipitation falling out of it. All right. All right. So what is precipitation? Simply water, H2O, solid or liquid, that falls out of a cloud. And what it's able to do is that it's able to overcome atmospheric buoyancy by something called its terminal velocity. Okay. In other words, gravity versus air resistance yields its terminal velocity. All right. You can see that. Pretty simple concept. Okay, so another thing to think about is the smaller and lighter this precipitation, like drizzle, the less its terminal velocity. The greater its terminal velocity, the large chunks of ice like hail, they'll have a much greater terminal velocity. And here's a chart that illustrates that right here. Okay, along the bottom, it gives the diameter of the precipitation, the size of it, and then the larger, you can see, if you look at the top, the terminal velocity increases from left to right. So you can see the type of speeds that these things are going to have to achieve, in other words, to overcome atmospheric buoyancy and fall out of the sky. All right, I'm going to talk about two precipitation processes. And the first one here is called collision coalescence process. Again, you want to think of a warm cloud here. This is pretty simple here. Water droplets will collide and coalesce. In other words, we'll get water droplets. Remember, they had to a condenser around some aerosol, type of aerosol. But now we've got a water droplet up there in a cloud. How do we get them to coalesce? And then they get bigger and bigger and bigger. They overcome gravity. They fall to Earth. All right, so how does that work? Well, first of all, the residence time of a falling cloud droplet inside the cloud is important. In other words, the thicker the cloud, the greater residence time that cloud droplet has in the cloud to collide with other cloud droplets to get bigger and bigger and bigger. So the thicker the cloud, the larger precipitation we can get out of it, and heavier precipitation we can get out of it. And I'm saying at the bottom, that's, for example, that's why raindrops are smaller when they fall from these thin stratus clouds, as opposed to when they fall from a very well vertically developed cumulonimbus cloud. And there's just a pictorial of it. As a cloud droplet starts falling through the cloud, you can see the precipitation droplet, the large droplet, and the little dots are the cloud droplets. But as it falls through the cloud, it's going to collide with these cloud droplets and start getting larger and larger. Okay, the second type of precipitation process, and I would refer to this as a cold cloud precipitation process. It's a Bergeron-Findesen process. Okay, sometimes you'll just see it as a Bergeron process. This type of precipitation is formed by ice crystals inside the cloud. So we've got ice crystals that form inside the cloud. And remember that these clouds, they can have supercooled water droplets in them. In other words, cloud droplets that are the temperature, they're liquid, but the temperature is well below freezing. But the instant an ice crystal comes in contact with one of these supercooled water droplets, supercooled water droplets freeze on this and tends to start producing a larger and larger ice crystal, a snowflake. All right. So think about that then. Cold precipitation process. It's when ice crystals form in a cold cloud full of supercooled water droplets, and then these supercooled water droplets attach to the ice crystal and produce snowflakes. All right, now once we get precipitation to start happening here, it's going to leave the cloud base and it's going to enter a part of the atmosphere where it's no longer 100% relative humidity. And it can be very dry. So it's falling through this unsaturated air, and it can begin to vaporize. All right. And in cases, particularly here in the Southwest, we can get a lot of situations like you see in this photograph where there's precipitation falling out of a cloud, but the air underneath the cloud base is so dry that this precipitation evaporates before it reaches the ground. When we get a situation like that, it's referred to in the third bullet, we refer to that as virga. So virga is precipitation that's falling out of a cloud base but evaporates before it reaches the ground. All right, so precipitation then, by definition, water in solid or liquid form that falls from clouds to Earth's surface. Now, you can see in the second bullet, we can get liquid precipitation. It's going to be rain or drizzle. The difference between rain and drizzle is simply the diameter size of the water droplet. We can get freezing precipitation. This is liquid water that falls through the atmosphere, but it freezes on contact with the ground. We call that freezing rain or freezing drizzle. All right. And then thirdly, we can get frozen precipitation in the form of snow, snow pellets, snow grains, ice pellets, hail, a lot of different types of frozen precipitation. All right. And you can see I've given you the diameters at the bottom there of liquid precipitation, the difference between rain and drizzle. In terms of snow, it's pretty complicated. You can look over here. You can see that there are 4 major categories of snowflakes. And we start with the warm ones, the needles, cooler dendrites, then even colder plates, and finally columns. So in other words, the type of snowflake produced is generally, not always, but generally dependent upon the temperature inside the cloud it's being produced from. All right. Okay, other types of frozen precipitation, snow pellets. Now, a snow pellet is when it falls, if you see a snow pellet, it will be white in appearance. It will be spherical in shape, so round in shape. And when it hits the ground, it doesn't really make a lot of noise. They almost look like little styrofoam balls, all right? So what my experience with snow pellets is it's generally going to occur in clouds where there's a lot of supercooled cloud droplets, all right? Snow grains are out of clouds. These are very small, by the way, snow grains. These are going to fall out of clouds that aren't that big, aren't that thick, and they're going to be very small, all right? Ice pellets, some countries call it sleet. I prefer ice pellets because the term sleet actually characterizes something different over in Great Britain. So it's really better to use the term ice pellets here. All an ice pellet is a frozen raindrop. Later on in the course, we'll take a look at how that forms. It's usually when a warm front comes in, this kind of thing, where we get temperature inversion where it's warmer up there. But anyway, rain will fall out of a cloud, then will enter a below freezing part of the atmosphere, and the raindrop will actually freeze. So these are going to appear as small little chunks of ice. Don't get it confused with hail. It's a frozen raindrop, an ice pellet. Freezing rain is showing you over here on this this upper air chart. You can see what it is basically showing you that as we go up in the atmosphere, you can see if you look at around, in this case about 900 meters, you can see the temperature is getting above freezing. All right, that's all it's showing. The dew point and temperatures above freezing. And then by the time we get up to about 700 meters above, or up to around 700 millibars air pressure, you can see it's going below freezing. The point of this graphic is this, that as we leave the ground, temperature's falling like we normally, like it normally does, but then it starts rising and actually gets above 0 degrees Celsius. It's just showing you the type of situation where we get freezing rain. So in other words, up where the precipitation is forming, it's above freezing. But then when it falls back to the ground's below freezing, so all the solid ground is below freezing. So as soon as this liquid strikes the ground, it freezes. So to get freezing rain to produce, we need to get a graphic like you see here, where on the upper air soundings, it's above freezing where the precipitation is forming. Okay, hail, as you can see here, this is totally different than an ice pellet. These are generally formed in cumulonimbus clouds in a thunderstorm. A very large, vertically developed cloud is what we need to have here. So what we get an ice crystal that forms, and then we get a big updraft. And the updraft carries this ice crystal further and further up into the cloud, where it comes in contact with supercooled water droplets. It grows and gets bigger and bigger. It might then start falling back down, but it get hit by another updraft and it get carried back up into the cloud. So its residence time is significant inside the cumulonimbus clouds, and almost layers and layers of ice form on these. Finally, when the thing gets heavy enough, it will fall out of the cloud. Now, we've had some very large hail stones recovered from the surface in the United States, some of which are in the 7 and 8 inch diameter range, so they can get very large. All right, that concludes this section on clouds and precipitation.